Well, good morning, folks. Welcome back to another session of Circuits and Devices. And we we started AC power last time, and we were talking about instantaneous and average power, and we also talked about maximum average power transfer, and we did some example problems. Whoops, that's not what I wanted to do there. And today we're going to go in and talk about effective or RMS power, and then discuss apparent power, talk about something called power factor and complex power. I know this sounds like a whole bunch of different things. It turns out they're all, very closely interrelated, and I'm going to show you some nice techniques for organizing them all into in fact, the notion of complex power is what ties a lot of this together. You'll recall that when we were looking at instantaneous power as well, we broke out and in fact we found that at any moment there is average power being transferred. The average or real power, which we called P, but there's also the reactive power that we called Q. We're going to see how all of these tie together: the real, reactive, apparent power, the power factor, and all of these things. And then we'll talk about power factor correction. Then a little bit about saving energy and AC power. So before we jump straight to looking at effective or RMS power, let's just briefly regroup on what we covered on this slide. Okay, hang on here. How do I get to this? That's what I want to do. So you'll recall that we looked at average power, sinusoidal analysis of average power. We said we took some sinusoidal source and we connect it to some passive linear network or a load, and look at the voltage across that load and the current through that load. And we referred to, we said, well, okay, we'll assume that we have some sinusoids, voltage and current sinusoids. Theta V is 0, the phase of the voltage, and theta I, we're just referring to as theta. Therefore, we just have to track, when we're looking at the phase difference between theta V and theta I. Remember, the two signals are not entirely in phase. Well, not necessarily anyways. They are, in what case, as a pop quiz question, what kind of load are the voltage and current entirely in phase? What must be true about the passive linear network if the voltage across it and the current through it are exactly aligned and perfectly in phase? That the network is purely resistive. There can't be any inductive or capacitive part in the net equivalent or Thevenin resistance, Thevenin impedance seen looking into that port. So at any rate, we're saying theta is the phase offset of the current, and then that's the phase difference between I and V. And we started with I just want to back up for a second so that we're going to introduce all these terms, but let's just ground ourselves in thinking back to where we started any of this, right? Power at any time, all of these the definitions we're going to introduce for these various kinds of powers: apparent power, real or average power, the reactive power. All of that comes back from just what we know about power in the first place. And power is still always defined as P is equal to I times V, the current through something times the voltage across it. Now that's the instantaneous power, right? P at any time, at any instant, is equal to the current at any instant times the voltage at any instant. So if we put in the sinusoids here, Im V max times the cosine of omega t, times the cosine of omega t plus theta, then we could we'd use some trig identities to rewrite this. And essentially, you can review what we did on Tuesday in the video there to go through the derivation. But the main takeaway is, remember that we arrived at a part, we arrived at a form where that this showed there was a DC amount of power delivered. Remember that on the last slide, we looked at this average, this instantaneous power is the graph shown here, the sinusoid in this burgundy color. The average power, however, is 1/2 Vmax times Imax times the cosine of the phase angle difference between the voltage and current sinusoids. Okay, that's that DC component, right? This is, like an offset. Remember, you go back to trigonometry, if you have some like vertical offset, what we refer to that in electronics, we refer to that as a DC component. That's the direct current component. Now, this is a graph of power versus time and not current versus time. So saying DC isn't quite correct, not a quite correct nomenclature. Because we're talking about power, but it's the offset in which that amount of power, if you were to average this function, right? If you average this, the parts above this line and the parts below this line cancel out. And so the average power is graphically represented as that dashed line. And when we went through this derivation, we saw that indeed, even though that there were these cosine and that these, the I times V ends up giving you this, Imax times Vmax times a couple of cosines with a phase offset. But if we use a little trig identities, we can actually tease out the fact that circled here in blue is this DC, or ever-present average component. And that's what we refer to as real power. It's the only power that's actually delivered to the load. There is other power being exchanged with the load, between the power source and the load, and that's kind of a continuous give and take of power, right? And we call that reactive power. So the component here, that this Imax times Vmax over 2 times the sine of theta, we call that Q. That's the reactive power. And we see that that's oscillating at this sine of 2 omega t term here. All right, so so I just wanted to remind us that we've already introduced this notion of real power. It's 1/2 times Vmax times Imax. Remember, these are the peak voltage, peak current, times the cosine of theta, where theta is the phase difference between the voltage and current phasors. We measure that in the units of watts. Q is the reactive power. That's 1/2 times the peak voltage and peak current product times the sine of theta, right? Not the cosine. And we measure that in volt amp reactance to just not confuse it with the units of watts. Okay, and then for reasons that'll become clear soon, we refer to the term cosine of theta as the power factor. And we're going to cover that today. All right, so what that does is leads us up to where we're going to go now. We're now going to talk about another kind of power called the effective or RMS power. Okay, and so down at the bottom, I have the definition from the textbook that says the effective or RMS value of a periodic current is the DC current that delivers the same average power to a resistor as the period current. In other words, if you took some, you looked at the average power, which we'll show here. So this is the effective value, and it's like, the way you want to think of it is how much power would be transferred to a resistor, to a purely resistive load. We call this the RMS value, and RMS stands for root mean squared, which we'll see borne out in the formula here. So let's say we have some sinusoid voltage, V of t is Vmax times the cosine of 2 pi over t. That's omega, right? 2 pi over the period t that's the same thing as omega. You recall that omega is equal to 2 pi over the period. And what we can write is VRMS, or what sometimes is also written as V effective, is equal to the square root of 1 over t times the integral from 0 to t of the square of the signal dt. Now this is true for any signal, by the way. You take any signal, it doesn't have to be the sinusoid that we're looking at, but take any signal and take the square root of it, which is the r. Take the average, right? 1 over t times the integral of a signal over time is the average or mean, and squaring the signal is a square of the signal. So that's what this means to be the RMS value. Okay, it's good to do that too, because if you think about it, the reason we're squaring it, you know, the average of a cosine signal is 0 over an equal number of periods. It's 0. That doesn't tell you much about the power that can transmit to a resistor, right? Because you know, that's still going to transmit an effective amount of power to a resistor, to some load. And so if we square it, then we get rid of the cancellation, right? So you square it and then take the average and then finally take the square root of that to undo the squaring that you've done. Okay, and so it gives you the RMS value. And if you were to calculate this for a sinusoid, or for the signal we're looking at, right? So now in red, we'll actually, in fact, let me do this in another color. Put this in purple here. So now we'll actually look at doing this for the sinusoid that we're working with here. This is 1 over t times the integral of 0 to t of Vmax squared times the cosine of, times the cosine squared of 2 pi over t times t dt. And if you were to evaluate that integral, let's see, I'll do this in, I don't know, let's say red here. Okay, if you were to evaluate the integral of this thing, right, this actually gets you, evaluating this integral would give you 1 over cosine of 4 pi over t times t over 2, evaluated from 0 up to t. All right, all to say that and when you finish the integral, this will be Vmax squared over t, and then when you integrate this thing up here, it turns out to be a t over 2. And so what we get then is these t's cancel, and you're left with the fact that the effective, V effective, or the RMS value is Vmax over the square root of 2. Okay, I do want to remind that this is for a sinusoid only. So if you were to look at the RMS or effective value for a square wave or a triangular wave, or the you know, sound coming out of my voice as I speak into a microphone, if you're measuring that signal, all of those signals have a different RMS value. And certainly the one from my voice does, because it's not very periodic, right? It's changing all the time. It's just ever dynamic. But you know, even periodic functions like a periodic square wave or a triangular wave or some other function, those are going to have different RMS values. So for this one, it is Vmax times the square root of 2. All right. The square root of 2 is 1.414, right? Okay, so if we were to open up MATLAB, where is MATLAB? Where did MATLAB go? Here it is, right? So let's say you had Vmax is equal to 1 volt. Okay, you have a 1 volt peak signal. VRMS is equal to Vmax divided by the square root of 2, right? Square root of 2 is 1.414. 1 over 0.414, right? Like 1 over 1.414 is, okay, it's a little bit of a round off there because I was using the square root function, but it's 70.7%. So when you look at a sine wave, if you were going to graph a sine wave, what I want you to think about, you know, this visually in your mind, what does the effective voltage look like for a sine wave? Let's say that here's your sine signal, right? And let's say this was Vmax, whatever Vmax is. Okay, here, oops, here we go. Here is, in fact, let me do this in purple so it matches here. If we were to look at 70.7%, here's 0.7% times Vmax. Okay, this is VRMS, right? So the effective voltage is actually, you know, sort of close to the peak voltage, but it's not the peak voltage, right? The peak voltage is in fact higher. It's 30% higher, or well, anyway, 70% of Vmax is VRMS. I didn't draw that Vmax very carefully here, but that should be something like that, right? Okay. So that's what the effective voltage is. If you were looking at a graph of current instead of voltage, then the effective or RMS current would also be, again, for a sinusoid only, would be 70%, about 70%, 70.7% of the peak current, right? Okay, so so that's effective or RMS power. Now let's talk about, oh, and by the way, sometimes this is written as V sub E. You might see it written that way. VE is V effective, VEFF is V effective, VRMS is another way to write it, right? Okay, so you'll see these different notations. I'll try to stick with, you know, VRMS probably, but anyway, okay, so so let's talk about apparent power. All right, apparent power. This is another variant of power we're going to discuss, and soon we'll relate all these together: apparent, real, reactive, and all this stuff. Okay, so so let's take, you know, let's say we had the you know, a voltage sinusoid here and a current sinusoid. In phasor form, we write them as Vmax at a phase angle of theta V, and the current phasor would be Imax at a phase angle of theta I. All right, the average power we've already shown. Remember, we reviewed this at the beginning of this lesson today, that it's 1/2 the Vmax times Imax, the product of the peak voltage and currents, times the cosine of the phase angle, the difference in phase between them. In other words, if you're looking at where my hands are, if they're perfectly aligned, they're like this, right? My right hand is let's say voltage, my left hand is current, and as they're phase shifted, there's a difference in they're shifted in time or phase angle, right? And we measure that in degrees, as we've discussed. Okay, remember, this is that DC, or, you know, average part that we pulled out from the instantaneous power. If we went all the way back to you know, this slide here, remember, looking at the instantaneous power, we, you know, pulled out, we used some trig identities, and we pulled out this constant portion here, that sort of DC or ever-present part, which we showed was this, graphically was this value here. That's the average or real power. And it is the only power that is actually transferred to the load, because the other ones are sinusoidally oscillating and exchanging energy back and forth between the source and the load. And we call that a reactive scenario, right? And we call that reactive power. Okay, so let's then talk about apparent power, right? So we've discussed that average power, that part we pulled out that's not changing with time, is 1/2 times the peak voltage and current product times the cosine of the angle between them. Okay, as a reminder, we could actually express this. So if, let's see here, so that's true in general, right? What I just wrote above there is true for any current and voltage waveforms. But if V and I are sinusoids, in other words, they're sinusoidal, we have the following. We can actually write P as V RMS times I RMS times the cosine of the phase angle between them. Okay, how did I write that as VRMS and IRMS? Well, just a gentle reminder from the last slide. Remember that we wrote, we could actually factor out this 1/2. We could write it as 1/√2 times 1/√2, right? Right, like 1/2 is equal to 1/√2 times 1/√2, right? So you can do that. And so we could actually write this as, Vmax over √2 times Imax over √2 times the cosine of theta V minus theta I. And we recognize that that this is in fact VRMS and this is IRMS. Okay, so we can write the average power, the real power, as the product of the RMS voltage and currents times the cosine of the difference between them. So thinking back to the definition for RMS, what did we say? The effective or RMS value is the periodic, or of the periodic current, is the DC current that delivers the same average power to a resistor as the period current. In other words, the effective or RMS power is how much power would be transferred to a resistor. Okay, so if you just look at the power, the RMS voltage times the RMS current, if it were truly just a resistor, that's what we think the power would be. That's what this power would be like. This would be, we call this apparent power. The apparent power. And we give that the term S, which I'll write here in purple. S is equal to VRMS times IRMS. And we measure that in volt amps. Again, we're not calling it watts because that's not the real power that's delivered. It's true that a volt times an amp is a watt, but we're writing it as volt amps so that we can distinguish the fact that that's not actually the power that is delivered to the load, unless the load is truly resistive, and then in that case, it would be. So we call this product, the product of the RMS voltage and RMS current, we call that apparent power. Okay, and there's a reason we call it that, because it seems like, or it would be apparent that the power should be VRMS times IRMS. Okay, however, it's scaled by this factor, right? If we look over here, but it's actually scaled. The real power, in fact, I should say the average or / real power, the power that's actually delivered, the one that actually counts at the end of the day, is actually scaled by this factor. By this factor is the cosine of theta v and theta I. And in fact, we give that factor a name. We call that factor the power factor because it relates the apparent power, what we perceive of the RMS voltage times the RMS current should give that much power to at least a resistive load. If it's not purely resistive, then there is a difference between the phase angle, right? Like if it was purely resistive, you could still put in cosine of theta v minus cosine of theta I, except that purely resistive loads, if you look at my hands here, are completely in phase. And so theta v equals theta I, and then you have the cosine of 0, and we all know the cosine of 0 is 1. So then the actual power delivered, the real power, P, is equal to the product of the RMS voltage and current. Okay. However, for non-purely resistive loads, it gets scaled by this factor, and we call that the power factor, and it's equal to the cosine of the phase angle difference between the voltage and the current. So let's talk about the power factor for a second. Okay, as we just showed, the power factor is the cosine of the phase difference between the voltage and the current. Okay. Now, so we can write this as, we're noting that P, the real power, is equal to VRMS times IRMS times the cosine of theta V minus theta I. And we refer to that as the power factor. This right here we refer to as PF. Okay. Now, VRMS, so we could actually write this, VRMS times IRMS, that's S, that's the apparent power, right? So we could actually write that, we could write the real power in terms of the apparent power. The real power P is equal to the apparent power S times the cosine of the phase difference between the two, the voltage and current waveforms. And we can then rewrite this and show that the power factor, another way to write it, is as the ratio of the real power to the apparent power, which then is also equal to just the cosine of theta v minus theta I. All right. Keep in mind that this is the actual power delivered. And that S is the apparent power. Okay, so the power factor is a measure of what fraction, how much of the apparent power, the RMS voltages and currents, is actually getting delivered to the load, right? That means the power factor can be between 0 and 1, right? That's I mean, the cosine goes between 0 and, well, it actually goes between plus and minus 1, but the phase angle between voltage and current is never, it's always between 0 and 90, right? And so the power factor is greatest when the voltage and the current are in phase. What I'll say last before we leave this slide is that the power factor is all about the voltage through the load. I'm sorry, the voltage across the load and the current through it, right? Because it's a ratio of the actual power to the apparent power, and the actual power, these quantities depend on the phasing between voltage and current. Well, that's the voltage across something and the current through it. That's analogous to, or another way to represent that is by the impedance of the load. So the power factor is also equal to the phase angle of ZL. So the phase angle is, so if you have ZL is equal to, I don't know, Z max times phi of the ZL or whatever. Phi of ZL is, I'm sorry, the cosine, my bad. This should have said it's equal to cosine of phi of ZL. It's the phase angle. So the cosine of this, of the phase angle of the load is also the power factor, because the phase angle of the load also is another way to say what's the phase angle of the voltage to the current, right? If the load is purely resistive, the phase angle is 0. If it's like purely capacitive, the phase angle is, I think it's plus 90 degrees, or is it minus 90 degrees? Let's see, it's negative J over omega C. So it's minus 90 degrees, right? The phase angle is minus 90 degrees. All right. Okay, let's continue on. We have some more derivations or definitions to go through before we can start to do some problems. And so I'm getting a question into the chat, and love this. Always love to get questions, help us enrich the discussion. So question says, does that mean AC power is not as efficient as DC power, since the equivalent DC current is a 0.7 of the AC current? Okay, that's an interesting question. So is AC power not as efficient as DC power? It's an interesting concept. Let me think about that for a little while, and I'll come back to addressing it in either a little bit later today or in another session next week, because that's a good concept. It does have to do with, if you think about it, you know, DC current is always pushing in one direction. The current never changes, moves back and forth, right? So, for example, if you're running DC current through an inductor, for example, you're always going to be getting the losses of the resistance windings, the winding resistance of that inductor, right? The inductor itself, the L part of the inductor doesn't really do anything, but the resistance of the windings in the inductor, let's say around 10 ohms, the DC current through that is always going to be losing energy. And so if you're worried about losing, so in terms of the energy lost in that, you might actually have a lower DC current from the AC, from the effective DC current IRMS than you would from a continuous DC current. So one of the things we'd have to do also in addressing this question is talk about the magnitudes. So I think if your question is getting at, because then we have to actually compare apples to apples, right? So is AC power as efficient as DC power? I think the question would be then, well, what voltage, what's the voltage, what's the peak DC voltage? Like, what is the DC voltage? Is it, let's say it's 10 volts. Okay, and then what's the AC voltage? Is it the peak AC voltage, V peak is 10 volts, or is it VRMS is 10 volts? And it should be VRMS, right, to compare apples to apples. And then when you talk about, is it as efficient as DC power, it starts to get into the concept of, well, what are you powering? We'd have to address that part of the question as well. Is it a purely resistive load? Does it have any capacitive components? Does it have any inductive components? And so, yeah, so the circuit would matter as well. And so, it does. We'd have to address it for a specific scenario. But those are really good questions, and let's continue discussing things like that and come back to it in a minute. Okay, so regrouping. We've talked about power. Wait a second. Hello. Okay, so we've now talked about effective or RMS power. We've talked about apparent power, and remember that's related to the average or real power. And then we've also discussed reactive power, which I don't have on this slide. But what I'd like to do now is introduce the notion of complex power. Okay, and this is the electrical engineers' method. Electrical engineers have come up with very inventive and creative ways to calculate and account for power, delivered, provided by and absorbed by elements and circuits. And this tool of complex power makes the analysis much easier, and it in fact ties together all of the apparent, real, and reactive powers and the power factor into a nice, simple one power to look at, and that's called the complex power, which we'll write as S. And so we'll note that S, the complex power, so we're writing it as a phasor, is equal to 1/2. It's defined as 1/2 the phasor voltage times the complex conjugate of the phasor current. Okay, and there's a reason why it's defined that way. So, engineers could have defined it as 1/2 the phasor voltage times the phasor current. That doesn't actually, defining it as the complex conjugate helps it to align with talking about leading versus lagging power and inductive versus capacitive loads. So it all aligns up correctly if you express the current as the complex conjugate, right? So that's just done by definition. Okay, now we can then write that as VRMS, the phasor times the complex conjugate of IRMS, right? Okay, and so what we'll do is then assume, okay, so that would be true for any signal. Let's now assume that V is a sinusoid, okay, and we can address it as V max at an angle of theta V, and we'll say that Z, the impedance of the load we're driving, because again it does depend on the load that we're driving, is Z at an angle of theta, right? Where theta is the angle of the impedance. Okay, so I then, the phasor I, is equal to the phasor V over the impedance. And we can then write that as V max at an angle of theta V over Z at an angle of theta. And what we'll recognize is that this value here is just I max, right? V max over Z is I max. And so we can then write this as I max at a phase angle of theta V minus theta. Okay, which then would mean that that the conjugate of that, I max conjugate, would equal, I'm sorry, the phasor I conjugate, the conjugate of the current phasor would be equal to I max at a phase angle of, we'd have to switch these. If it's theta V minus theta, then this would be theta minus theta V. Okay, so if we then go and calculate S as equal to, this is equal to 1/2, we'll plug in the phasors here, 1/2 V times I conjugate. So this would be, if we plug in the phasor, here's V max at a phase angle of V times I max. Oh, and this is the phasor I conjugate, right? So this is I max at a phase angle of theta minus theta V. And you'll recall from the way that phasor multiplication works is that if you have two phasors multiplied by one another, the product of those two phasors is a new phasor it has the magnitude, which is the product of the magnitudes, and it has a phase angle, which is the sum of the phase angles, right? So what we get then is that this is 1/2 times Vmax, so the product of the magnitudes is Vmax times Imax at a phase angle of the sum of the phases. This is theta V plus theta minus theta V. So the theta V's cancel, and you're left with just a phase angle of theta. All right. So that's shown in polar form, right? In magnitude and phase form. If we now then write that in terms of in rectangular coordinates, this is 1/2 Vmax times Imax times the cosine of theta plus J times 1/2 Vmax times Imax times the sine of theta. Okay, and what we see then is that here's 1/2 Vmax Imax times the cosine of theta. We actually already know, right? We've written that out before. P, the average or real power, is 1/2 Vmax times Imax times the cosine of theta, and we've actually already defined Q earlier in the earlier slides as 1/2 Vmax Imax times the sine of theta. And so we actually see that this is S is equal to P plus J times Q. So the complex power S, which I've shown as a phasor because it's in the complex plane, is the complex, vector sum of the real or average power plus the reactive power on the J axis or the imaginary axis. So so in other words, I mean so that's what we have there. So then so what we can do then is actually tie all this into a nice geometric relationship to relate all these things. And that geometric relationship is referred to as the power triangle. And it's a super useful thing in helping us use trigonometry of right triangles to calculate real and reactive and apparent powers, and then also, as we'll see shortly, be able to do some power factor correction. So let's go ahead and write this down here, that P of t, the signal as a function of time, we've now shown is P, the real power, right? This is that 1/2, as we just showed on the back here, this is that 1/2 V peak times I peak times the cosine of theta. All right, so P times 1 plus the cosine of 2 omega t plus Q, the reactive component, times the sine of 2 omega t. Okay, and then we can write this down just so that we remember here on this slide where P is equal to, myself a little more room here, P is equal to 1/2 Vmax times Imax times the cosine of theta. Remember, theta is theta V minus theta I. We could also write that as VRMS times IRMS times the cosine of theta. And Q is 1/2 Vmax Imax times the sine of theta, or we could write that as VRMS times IRMS times the sine of theta. Okay, power factor, as we've shown, recall, is the power factor PF is equal to the cosine of theta. And we've actually also shown that, what have we also shown? We've also shown that P is equal to S times the cosine of theta. We showed that back here on this power slide, right? On this power factor slide, right? The average power is or the real power, average or real power, is VRMS times IRMS times the cosine of theta. That's S, right? Okay, in fact, I think we just wrote that on this slide, right? This term right here, just always remember that that's S. VRMS times IRMS is S. So we can actually show that P is equal to S times cosine of theta, and Q then is equal to S, right? This whole term there is S times the sine of theta, right? And what we see then is a right triangle relationship showing up here that we refer to as the power triangle. And it takes the real power, P, and the reactive power, Q, and plots them in the complex plane. Right, so this is in the complex plane. And S is the is the complex power, and theta is the angle between S and the horizontal or real axis. Right. Remember that this is. I guess I can just write it like this, right? This is the real axis, and this is the imaginary axis. Okay, so Q is the reactive power. We've sort of seen that already. S is the complex power. Remember, that's equal to S is equal to P plus JQ. And then P is the real or average power. And you know, recall that that is the power that's actually delivered. Okay, I know I've said some of these things like sort of several times and reiterated and rewritten some of this stuff. I hope that it's helpful. That's the intention. I know there's a whole bunch of different terms here. And it's helpful for us to remember what's what. Before we move on to, I believe we're starting in on some examples now. So finally, we'll go and actually use some of this stuff. Before we do that, I actually want to take a look at the power factor, or at the complex power for a couple of different common kinds here. So if you have, let me actually draw this in black here. So again, this has to do with, you can't talk about the power of a source, right? That's not really the correct nomenclature to say it that way. It's going to be the power of a source delivering to a load, right? So this has to do with essentially a load, and you can analyze these. It's a relationship between the source and the load. So knowing both of those things, you can then start to look at the power or the complex power. And so there's a couple of different ways this could work out. You could have a complex power S, right? This is, remember, this is, what is it? That's the, you know, it refers to, if we're, you know, just a reminder that this is the complex plane. Here's the imaginary axis, here's the real axis. Okay, so let's say you have some complex power S. That means there's a real part, right? This is P, that's the real power delivered. And then there's a reactive part. And in this case, this would be a positive Q. Okay. And we say that a positive Q, a positive reactance, is in fact a lagging power factor. Which means that the I believe the voltage is lagging the current, and that's an inductive load. Okay, and so this Q, this amount of power here, is in fact how much energy is being exchanged between the power source and the inductive portion of the load. Whereas the real power, the horizontal component here, is the only part that's actually transferring power to the resistive part of the load, which is, ultimately at the end of the day, what counts. Okay, so let's then talk about another scenario. You could, so when S is in the first quadrant, you have a positive Q, a positive reactive power, and that's associated, we refer to that as a lagging power factor, right? So that's a positive angle theta, right? Plus theta. And we associate that with inductive loads or predominantly inductive loads. Even if there are capacitors in there, if the inductance plays more of a role in the circuit, and again, that's going to be frequency dependent, but if it's more inductive at the frequency it's being excited, then the complex power will lie in the first quadrant of the complex plane. If, on the other hand, the load at the frequency it's being driven is predominantly capacitive, you'll have a complex power in the fourth quadrant with a negative Q. Okay, and we refer to that as a leading power factor, which we associate with a predominantly capacitive load, and it has a negative theta. Okay, you may be wondering, well, what about the second and fourth quadrants? That would indicate a negative. You can design an element to have a complex power in the second and fourth quadrants, but it requires having a negative resistance, right? The real power would be a negative power, and that's in fact associated with a negative resistance that actually, gives power back to the system instead of absorbing it from the system, like a speaker, right? An 8-ohm speaker takes electrical energy from an amplifier and turns it into sound, but the energy is lost from the electrical system and transferred to the acoustical system, right? And so that's a positive real power. The power is taken out of the electrical system and given to the acoustical space, right? The air or sound or whatever, air or water or whatever medium this speaker cone is pushing. That's energy transferred out of the electrical system into the acoustical and mechanical system. Okay, now you can design elements that have negative resistance using active elements like op amps and transistors and stuff like that. And if you're interested in that, there'll be opportunity to study that in later courses and circuits if you're an electrical engineering major. All right, let's finally get into an example. So here's a circuit. And it's got a couple resistors and a capacitor, and we've been asked to find the power factor, and in part B, which we'll do on the next slide, we've been asked to find the real or average powers, the reactive and the apparent powers. Okay, and let's note a couple of things before we get started. The capacitance has already been the impedance of the capacitor has already been calculated, so we don't know what omega is. But it doesn't really matter. It's already been calculated. The impedance of the cap has already been calculated. Okay, and so for part A, we'll recall that the power factor is equal to the cosine of theta. All right, where theta is the phase angle between the voltage and the current, but it's also equal to the phase angle of ZEQ as seen by VS, as seen by the voltage source phasor. So this is ZEQ, the equivalent impedance seen looking into that network. And so we can then go and calculate this. ZEQ is equal to, what do we have? We have a 6 ohm resistor here in series with a negative J2 parallel 4 ohms, right? And so if we wanted to, just for practice, if you wanted to calculate what that is, remember you would say this is 6 plus the parallel combination is negative J2 times 4 ohms over negative J2 plus 4 ohms. And if you went and calculated that, again, what I would do is put this into MATLAB. And I think I already calculated this. I called it Z Thevenin instead of ZEQ, but you'll see that this is 6 plus 4 times negative 2J over 4 minus 2J. And if you calculate that, you can see what it is in rectangular form. And if you use those functions that I've been recommending that are posted on the Canvas page, if you look at the mag phase of Z Thevenin, remember that's a function that we've added into our library. It's here, magphase.m. This will convert it into magnitude and phase form. So it's about 7 at a phase angle of negative 13.24. So this is 7 at a phase angle of negative 13.24. Now, notice that we see this is a negative phase angle. And so this is predominantly capacitive. Okay, is that any surprise to us? Not at all. There are no inductors in this circuit. There's only one capacitor. And so we expect, in fact, the phase angle of the impedance to be negative, at least by some degree. Now you'll notice that it's only 13 degrees below the horizontal axis. So it's, you know, if you're thinking about the amount of power, the power factor is fairly substantial. If the phase angle is really close to 0, 13 degrees is not very steep, right? 13 degrees below the real axis is it's not 0, it's you know, fairly close to 0. How close? Well, that would depend on, you know, kind of relatively. But if we then look at the power factor and then answer part A, power factor is then just the cosine of that angle, cosine of negative 13.24 degrees. And if you calculate that, it tells you that the power factor is 0.9734. Okay, not bad, right? So that means that 97%, so the amount of power being transferred to this entire load here, right? That entire load, the 6 and 4 ohm resistors and the negative J2 capacitor, the entire power delivered to that load from this 30 volt VRMS source is 97% of what it would be if the load was purely resistive. All right. So that actually is that a question? Okay, so it's good to think of the power factor in those terms, you know, right? So like this is transferring how much power? It's transferring 97.3% of how much power it would if of the apparent power, right? If it was purely resistive. Okay. Oh, and then also we can just write ourselves a quick note that this is leading. All right, now let's actually calculate the real and reactive and apparent powers. Okay, so for this part, we're going to look at, we need to find out the current. right? If we want to know the power, we need to find the voltage times the current. So let's start by giving some phasor names here. This is going to be V1, okay? And notice that this is already given to us in RMS form. So VP, 30 volts, so I should say Vmax is not equal to 30, right? It's VRMS, at least the magnitude of it, is equal to 30 volts. All right, so make sure you're keeping track of, when you're looking at problems, do check and see if this is shown as an RMS value or if it's a peak value. All right, so we're going to call that V1, and we'll call the current flowing out of the source, we'll call that I1. All right, so part B here, we're going to say that V1 is 30 at an angle of 0 degrees, and we'll remind ourselves that that's in RMS form already. I1 then, the phasor, which is going to be RMS, right, is equal to V1 over ZEQ, the equivalent impedance that we already found in the last part of the problem. Okay, so we'll put this in here, and it's 30 at a phase angle of 0 over 7 at a phase angle of minus 13.24 degrees. So 30 over 7 is a little more than 4, right? 28 over 7 is 4. And so this ends up being 4.286 at a phase angle of positive 13.24 degrees in amps. And again, that's RMS. And so now we want to go ahead and calculate the apparent power. And once we know the apparent power, in fact, I take that back. Let's go ahead and calculate the complex power, because the complex power will tell us, once we know its form in mag phase or polar form, and we know it in rectangular form, that's going to tell us everything we need to know. It'll tell us the real power. It'll tell us, when we see it in mag phase form, it'll tell us the apparent power and the phase angle, and then we'll extract the real and reactive powers from it in rectangular form. All right, so here's the complex power. Remember, it's the RMS voltage phasor times the complex conjugate of the RMS current phasor. So this is 30 at a phase angle of 0 degrees times, okay, so we'll put this in parentheses, times the current one, which we just calculated, that's 4.286 at a phase angle of 13.42 degrees. And if you calculate that out, you'll find out that this is 128.58 at a phase angle of, it's got the same phase as the current. And we say that's in volt amps because it's complex power. Now, if we wanted to convert that into rectangular form, you could do a couple of things. Let's see, how did I do this? I actually put together a short script in MATLAB to calculate this problem. We have Z Thevenin calculated here. Here's the voltage and current phasors. By the way, this is in RMS. And so this is V1 is 30 at an angle of 0 degrees. I1 is V1 over Z Thevenin. I was calling it Z Thevenin in this one instead of ZEQ, but okay. Then I just displayed it in mag phase. I calculated the apparent power. So the apparent power S is V1 times the complex conjugate of I1. And in MATLAB, if you have a complex number, if you put the prime after it or the apostrophe, it'll give you the complex conjugate. Okay, and then we show that value in magnitude and phase form, which will give us the value that we just got here, 128.58 at that minus 13 degree phase. And then if we want the real and reactive powers, one thing I could have used the built-in function we have or the function we've included. I think it's angle. No, actually, that doesn't give us, it's not quite what I want. I want the real and reactive powers from S. And so I just use some built-in MATLAB functions. I say P is equal to the real part of S, of the complex power. Q is equal to the imaginary part of S. And so real and imag are built-in MATLAB functions. And they'll just extract the real values and we'll display them. So if I run that, problem here, example 11, an AC power, here it is. And we could also get to this by just, using trig on the complex power. And so this shows us here's the current, here's the power we calculated, and then here's the real and apparent, or the real and reactive powers, 125.4 watts and negative 29.5 volt amp reactance. So we can then write this as we've just pulled that out. This is 128.58. If you wanted to calculate it by hand, you would put it in like this, like times the cosine of negative 13.24 degrees. Okay, right? So I just used MATLAB to do this, right? Extracting the real part, that's the same as just taking the magnitude and multiplying it by the cosine of the phase angle, plus J times the imaginary part, which is going to be 128.58 times the sine of the phase angle, right? So if you want to do it that way, you can, or you can use MATLAB. My preference is MATLAB, especially because you can go back and change your, adjust this in case you made any mistakes. But this is this gets us 125.16 minus J times 29.25. So again, we saw that we saw those same values in MATLAB. Here's the 125.4 and the minus 29.5. And so the answers are that the real power P is equal to the 125.16 watts. The reactive power, that's Q, is equal to the minus 29.25 volt amp reactance, or VARs. And the apparent power S is equal to the magnitude of the complex power, S bar, the phasor. And that's, we already saw, that's 128.58, which we refer to as volt amps. And that's our answer there. Now, before we move on to look at anything next, what we should recognize is that 125.16 watts out of the apparent 128.58 volt amps is delivered to the load. That's synonymous with seeing a relatively high power factor. 97.34% of the load, of the apparent power, is transferred to the load. And in fact, if we took the magnitude of S, so I believe I have S shown here as one of my variables here. MATLAB will show it by default as in rectangular form. I believe if I actually just calculate magnitude of S, so I'll just write this as S mag equals magnitude of S. That's a built-in MATLAB function. Whoops. Oh, sorry, I meant to say abs S. let's just clear this out. So the magnitude of S equals absolute value of S. And you'll see that we get this 128.54 or 128.83. And that's, in fact, exactly what we got here, 128. Well, I thought it was 5.3, but or 5.8. Maybe I've got some rounding going on here. But anyways, if we were then to take a look, remember the power factor, which I did not calculate there. I should have. The power factor is 0.9734. So if we write that in here, PF is equal to 0.9734. And then we look at P, the real power, P real, which will just differentiate from the stored variable I have P. The real power should be 97.34% of the magnitude of S, and there it is, it's 125.4, and that's, I believe, what we saw here, 125.16. Again, there's some rounding error here, but I just wanted to go through that, that analysis so that you can sort of start to feel the connection between the magnitude of the apparent power, or rather, that is the apparent power, the magnitude of the complex power and the real power. Again, they're related by that power factor. Okay, so one of the things that you want to do, and I'll just introduce this topic and we'll finish it on, we'll finish this chapter on Tuesday, is to be able to correct the power factor for certain loads. All right, as I've got listed up here in the upper left, is that a lot of different kinds of loads, electrical loads, are inherently reactive. And a lot of the time they're typically inductive because they are made with things that have windings in them. Why are those windings in there? Well, there are transformers that, you know, they are used to galvanically isolate certain circuits. What that galvanically means is that they're not connected by metal, right? Galvanic connection. So they're used as isolation devices. They're used to increase the voltage or current, respectively. Or there are motors or generators in these, and especially in lots of like home appliances, like domestic loads, like washing machines, air conditioners, and refrigerators, all use motors in some way to either spin things or you know, energize pumps and stuff like that. In industrial loads, you'll see induction motors. So, you know, or in a Tesla car, for example, or any kind of electric vehicle, you know, those are powered with electrical motors, and all of those are done with windings, right? They're made the way you know, create an electrical motor or a generator, which are very similar in nature, is you have a coil and you would run electric current through it, and it's nearby a magnet, and there are magnetic forces between them which cause it to generate, you know, mechanical motion. Okay. Anyways, takeaway is that many loads are inductive in nature, and so it turns out that you can correct the power factor. Remember, the power factor tells you what you want ideally is as much of the apparent power, the effective RMS voltage times the current, as much of that transferred to the load as possible. And what you can do is, if you have a large angle between voltage and current, you can start to reduce that. And if it's primarily an inductive load, adding some capacitance in parallel actually can, inductors are going to have a positive reactance power. Capacitors are going to have a negative. They're going to introduce a negative reactance, and that can actually bring the voltage and current waveforms closer to in phase, and in fact increase the energy efficiency of your device. So when you see, like, on you know, modern devices today, it's like a Energy Star efficiency, and they're marked for that. You know, good effort has been made to correct the power factor of these devices. There's other things that goes into it as well. You can increase the efficiency using other mechanisms as well, but certainly optimizing the power factor is one way to do that. Okay, so we'll look at examples of that on Tuesday when we regroup, and that will finish off chapter 11 for us. You should be able to do most, if not all, of the homework, the last homework assignment. We are going to cover the very last piece on power factor correction, which I think there's 1 or 2 problems at the end of the assignment, and we'll do that on Tuesday, and you'll be able to finish that up next week. If you want to jump ahead, there's good examples in the book that you can check out. But we'll cover that on Tuesday. So that wraps up this session and our discussion for the week. Have a great weekend, and I'll catch up with you on email over Canvas. So, until next time.